Thank you, Andrea. Thanks for this opportunity. So yesterday, we launched a new initiative here. We had a workshop, a virtual workshop on the mathematics of machine learning. So that is a big workshop. I have a new Muri, just like I had with the fractional PDEs before. Now the Air Force is supporting it, and we have about 70 people attending from all the agencies, because there's a tremendous interest in scientific machine learning, and especially in understanding the mathematics or develop new mathematics for artificial intelligence and neural networks specifically for problems in science and engineering. I wanted to start with this intriguing picture of my espresso cup with thermal gradients showing above it, and one of my questions, which is sort of the theme of this talk and our work, is, can you solve ill-posed problems? Like, can you pose a question like, can I quantify the velocity and pressure field above my espresso cup? It's not such an important question from the engineering point of view, technological point of view, but obviously it highlights some of the difficulties in doing that with conventional methods. We don't have a way. If I don't give you the boundary conditions, if I don't give you the equations, if I don't give you lots of information, then you cannot infer anything. But I will try to show you that I can actually do some things, and in fact quantify from experimental data and come up with answers. So I will show you some of the examples, but before we go on, I want to give you, by the way of introduction and an outline, a glossary. There's lots of acronyms here. So I want to talk about PINs. These are physics-informed neural networks. I will talk about that first, and then I will talk about DeepFNet for neural network for functional approximation. We move on to operator approximation and DeepONets. And my favorite one, how sweet it is, DeepMNM, a neural network for multiphysics and multi-scale problems, how we use DeepONets as building blocks, pre-trained networks, to solve really tough problems, like, for example, in hypersonics, a very hot topic right now, at least in the United States. I will show some theorems, so let me start with the standard universal function approximation theorem. This was developed by George Saipenko in 1989. He was assistant professor at Tufts University. There was not a lot of interest at the time, but there was a sort of a second or third wave, depends on how you count, on neural networks and artificial intelligence. So let me start with this. For those of you who have never seen this before, it's a fundamental function approximation. It's just an approximation theorem. There are other errors when we use neural networks. I will talk about that. But basically, you have ax plus b. These are the weights y. These are the biases. This is an x. And then we pipe that through a nonlinear function. It should not be a polynomial. So it could be a sigmoid. It could be what we call ReLU, like a RAM function and other type of functions. And then you have these ways to find nothing unusual, nothing from what we are used to see approximating a function. The basis is a nonlinear, however, and the theorem says that a single hidden layer, so g of x will be here, the output. This is the neural network for g of x. G of x is aj's are basically this here. Yj's are these connectors, which denote weights and biases. So if you have enough data, you can approximate arbitrarily close this function g of x. Okay, there's a lot of work in the early 90s by Hornig, Maskar, and other people on approximating functions, approximating also their derivatives, because that's very important to also be able to approximate, to have a universal approximation of differential operators. Then that brings us to partial differential equations. One of the questions that we are interested, I'm personally interested right now, is, can you approximate discontinuous functions? There has been some work on it. However, if you try to do a single neural network, you will not be very successful. It turns out that deep neural networks are more expressive. This is what the third generation of neural networks has provided us, expressivity, and of course faster training using better hardware, in trying to regress, to express functions which are more complicated. I want to show you what happens if you try to approximate a discontinuous function. It turns out that these weights yj could explode In fact, if you're trying to solve a problem with a discontinuous solution, you may not be very successful. However, one can extend, and one of my postdocs has done this very recently, can extend this theorem to a universal function approximation with bounded weights. Why would you want to do that? Is because you have a better approximation. I want to give you a little bit of math just to start. I want to emphasize how important math could be. That's the purpose of this slide, is not to show you the entire theorem, but it's basically to show you that if you want to do a approximation using neural network, whether you put a bounds on the weight, let's say all the weights yj has to be, and the bias has to be less than 2, then you can develop some theory that will give you a specific architecture, a specific neural network architecture, a deep neural network with several latent layers. In fact, you can dial in how many layers, and then you can decide how many neurons and so on. Just to make things concrete, my plan here is not to give you the exact theorem, it's just to give you a highlight of what you can do. For example, imagine you want to solve this advection equation, du dt plus du dx of this waveform, and you do that for long-time integration. You can see how nicely a neural network approximates this with no limiters, nothing. This is a deceptively simple equation, but what I want to show you is that the neural network I use here came from a theory, and my inputs are 2, x and t. My output is 1, is the solution of this linear advection equation. If you look here inside this bracket, I don't know if you can see my cursor on the right underneath the movie. I have the number of neurons per layer. So it's something that a human would not be able to do. In fact, if you start having 20 neurons per every layer, you'll get a lot of wiggles, and you will not be able to simulate even this simple stuff. So the message here is that you can dial in what the theory can give you, which is totally lacking right now because there's a lot of empiricism out there, even for in our field in scientific machine learning. But what this theory shows you, that if you require a certain degree of accuracy in your approximation, if you know the number of discontinuities in this particular case, and the polynomial degree by which you want to, or the equivalent that you want to approximate this, you can actually come up with theory that will give you a priori an architecture that will guarantee that you will not have explosive weights, that you will not have overshoots and undershoots, you will preserve monotonicity, and you can have very, very small dispersion errors, as I show you in this simulation. So that's by the way of introduction. I want to move with the main topic. I don't want to give you the idea that 50 or 100 years of work on scientific computing is totally lost because of these new methods. But because what we have been, but I want to emphasize that we've been looking at something different now. What we have looked at the past collectively as a community, the scientific computing community, in the numerical analysis community, is things like that. If you look at this left box that I have, I say we know a lot of physics and we have small data. This is a case where we have a nice, well-posed problem. We know the PDE, it's well-posed, and I need some data for my boundary conditions and initial conditions. Unfortunately, for people like me who work very closely with applications, this is not the case. What you have more often than not is this middle picture. It's a picture where we know some of the physics. We may know the PDE, but we don't know the parameters. We may not know the boundary conditions. We may have data elsewhere. So especially for multi-physics problems, we may have some data for some state variables, but not all. Even if you know the physics, like the open problem of turbulence, you may not be able, even with exaflop computers, to resolve the small scales. So you need some data for the closure. So this middle picture is a realistic picture. And that's where the convergence of numerical analysis and scientific computing would come in, and PDEs in particular. Now, on top of that, the data that you have is not ideal data. I work very closely with the Army, and when I visited there recently, they gave me this 5D law. You see all these words start with a D. Dinky, if you don't know the word, it means small. Dirty they use the word dirty to mean noisy data. Dynamic to mean the data is streaming. You don't have the data there to play with for a long time. And then deceptive, they said, because be aware of Russians. They're always there. And data. So in other words, here's the big picture. I know some of the physics in the problems I'm trying to solve, and I have some data, and this data is multi-fidelity, multimodality, because I can have data from different types of sensors, images, and so on. I'm not going to talk about this problem on the right, but it is possible if you have a lot of data to also discover the laws of physics, and there's a lot of work on that in my group and other groups around the world. So this is how we integrate data and neural networks, which means functional approximations, solution approximations, and physical laws. This was in this paper that lots of people are using now. As you can see, it's a very, very simple concept, and I want to take you through that. A neural network, as I discussed before, I show you a neural network schematic with U being a function you try to approximate. Sigma will be the activation function, and XT will be the input. As I said, if you have a lot of data, you can, by minimizing this term that I have down here on the right, it's the mean square error, mismatch between the data and what the neural network predicts, and by iteration and by backpropagating the error. Here, you can find all these links. You can find the weights and the bias. You can find this approximation that I talked about in the first theorem. However, we don't, in science, we don't have enough data. We never have enough data. And as I said, the data is not of the same fidelity, not where I need it. But we know that if we solve solid mechanics problems, if you solve quantum problems, you do have some conservation laws. You do have some governing equations. In this particular case, I pretend that I know that U satisfies also the nonlinear Schrödinger equation, let's say. And as you can see here on purpose, I write my equation. F will be the residual, which I want it to be 0. But I write my equation in such a way that I pretend that I don't know some of the parameters. So I know that U satisfies a conservation law, but I may not know the entire conservation law. It may be in a parameterized form. So again, this is the middle picture I show you. I have some data, and I have a manifold. I have a residual that I'm trying to minimize. So down here on the bottom, I also try to minimize the residual using least squares, F minus 0 square, and I want to evaluate that residual at some random points. So at the end of the day, I have something really very simple to minimize, namely a weighted sum of the error, the misfit in the data, and misfit in the conservation law, the fact that my residual, if I plug in a data-driven U in the conservation law, it will not satisfy the residual being to 0, but I want it to penalize that residual to be 0. You can have weights in front of the data and the physics, but that's the balance between data and physics. What makes this interesting is that very simple to implement, because after you do that, you just use standard minimizers that Google and Facebook and so on are using. But the point is to formulate this problem properly. Also, what is interesting is that if you have a lot of data and very little physics, you go to an inverse problem. If you have a lot of physics and very small data, you go to the classical paradigm of well-posed problem with very little data, just the boundary conditions. So without doing anything, just by balancing data and physics, you can solve forward, inverse problem, or something in between, hybrid problems. So it's the same formulation, will be the same code also. That's why the industry loves it. The industry, and I work with all the big companies. NVIDIA actually has an implementation of what I will show you here. ANSYS is the largest company, software company in the world, and Siemens are working on it. So the industry likes it. Also, the professor likes it because they say it's so simple, I can improve it. So lots of people these days write to me to say how simple this is and how they did much better than what I did before. And I'm very happy, actually, for both sides, because the industry implements it, and then there are lots of professors and students who work on it these days. Let me illustrate this concept, the simple concept, with trying to solve this viscous Burgers equation. Andrea, can I have a A thumbs up for you. Can you hear me? And so far, everything's okay?
Yes, everything is okay.
Okay, bene. All right.
Sorry. Do you mind to push hide on the bottom of the slide near to stop sharing?
Yes.
Thank you.
Sure. Thanks. Any feedback will be good, useful. Thank you. So, because I usually use Zoom, I never used this before, but it seems to work fine. Thank you for the suggestion. So let's demonstrate how difficult this is for a student or even a professor. My joke is that this is so simple, even professors can program their own ideas now. Let's say this 1D, the viscous-Burgers equation. How would you implement that? Well, use TensorFlow, which is like the MATLAB for neural networks. You define the neural network. This first statement is just one statement. You can see TF stands for TensorFlow. You define the neural network on the left, okay, with weights and biases. Then you're trying to define the residual. The residual has a term U, it has a UX, UT, and so on. So you just take TF gradients. In other words, if I go back here, if I go back here, you see I have a neural network on the left and I have a neural network on the right. I don't show the connections of the right because the way I implement this differential equation, I actually use automatic differentiation to take derivatives of U and in time and second derivative and so on. So every time I take a derivative of U, this neural network, the graph of this neural network becomes very complicated. It's a nested graph that Google and other companies have implemented in their automatic differentiation packages. But I use that because automatic differentiation is used anyway to backpropagate the gradients of the loss function, the objective function, for this optimization loop, and using stochastic gradient descent, for example. So I use exactly the same technology. Therefore, I don't need finite elements. I don't need finite difference. I don't need any standard numerical methods to discretize my differential operators. In fact, I never discretize X. I never discretize T. So that makes it sort of precise, if you like. But it makes the neural network very deep because every time I take a derivative, I double the size of the network. So if I start, let's say, with a network of a length of the number of layers being 10, then I ended up for this equation having a deep neural network with 40 layers. So it's relatively harder to train. But nevertheless, the implementation, as you can see, is less than 10 lines of code. I have to clarify a few things. When you see here in this XT domain, as I said, I don't discretize T. T is still a continuous variable. I don't discretize X. It's still a continuous variable. X and T, I have to compute the residual at all these points inside, random points inside the XT domain. I don't separate X and time. And then I have to compute this term on the residual and weight it or not weight it. I can form my loss function. If I arrive at this point, then I call my favorite Adam minimizer that is off the shelf. And then just a few minutes later, I get the solution. So from scratch, basically within an hour, you can find solutions of this, even if you're a novice. Notice also that here, for the boundary conditions, I didn't use data continuous in time. In fact, on purpose, I use random data at the boundaries to show you that this method is immune to boundary conditions. So I can solve a boundary value problem without boundary conditions. I'll show you later some mathematics behind this. Now, as I said, it's simple, but it's also a very robust and flexible way of solving PDEs. Now, the same equation, I can solve this in the XT domain, and I can do domain decomposition. So the all good domain decomposition comes in handy, except it's simpler. One can use ideas from finite elements and finite volumes, discontinuous Galerkin, and so on. And we have versions like this, but one of my postdocs recently proposed this new X for extended pin, where we can basically take the XT domain, the space-time domain, we can discretize it, as you can see here, in an arbitrary fashion. The reason we chose a dolphin and a blue sea is to demonstrate that you can have really fun shapes in your domains, convex and non-convex domains. So now the blue domain is one neural network. The dolphin domain is another neural network. And how do we glue those together? Well, typically, for a second problem like that, I would need also the function and the fluxes and so on in the variational context. But here, I only need to have my residual being continuous because I know the residual is 0 everywhere. So the stitching is very simple. The flexibility is tremendous because in every neural network, you can use different activation functions, different points, in fact, different GPUs, and you can do it in parallel. So if you divide this into 100 domains in space-time, so now you can do parallel in time, you can have a speed-up factor almost 100 because the communication is only communicating the residual, not fluxes, no other, you don't take normal derivatives and so on. And down here, you can see that is really a seamless, if you can see here on the right panel, where I have the solution, right here, the middle is where the steep gradient is, but you see no errors, for example, where the sim is, namely the how I glue the one domain versus the other. So XPin is a very general domain decomposition. We haven't put that in the archive yet, but the paper was just accepted. It's a very simple idea. In fact, when we first submitted this paper, it was rejected by one of my my good friends as an editor. He said, this is very simple. It's useful, but very simple. So I said, that's exactly what we want. We want simple methods that people can implement. A few months ago, we published a paper in Science where we demonstrated how we can solve ill-posed problems in mechanics, fluid mechanics and solid mechanics. For example, in here, I consider the classical von Karman street behind a cylinder. But I'm not solving the forward problem. I pretend that I have this, given the data that is given, is a patch of dye, or smoke, which is in the wake. So I have a video of that. Can you infer the velocity field and the pressure field where I have these snapshots of this flow? I don't know anything about the Reynolds number. I don't know anything about boundary conditions. Somebody gave me data from an experiment. Can I infer the velocity and the pressure field? The answer is yes. If you know the governing equations, like the passive scalar equation for the dye, the Navier-Stokes equation, the compressibility constraints, all this, again, you don't need a grid. You remove the tyranny of mesh generation. For real applications, let's say for an airplane wing, it may take weeks and even months to do that. Here, you just remove that. Everything is done with neural networks with automatic differentiation. And indeed, if you train this neural network, and the data now is on the auxiliary field. We call it hidden fluid mechanics because it's an analog with a hidden Markov process. In hidden Markov processes, we have auxiliary data, and we're trying to find primary quantities. Here, I'm interested in velocity and pressure, but I'm given no information whatsoever on the pressure boundary conditions, on the velocity boundary conditions. So I'm able to infer the velocity and pressure in time for that patch of dye. If the dye goes around the cylinder, I can even compute the forces on the body, which is something very practical thing that the engineers want to do. This is something else that is very timely. I don't know if you can see my movie. It's a Schlieren photography from this company, LaVision. We first found this on the YouTube, and we said, can we quantify the velocity field and the pressure around the mouth and the nose of this person who is puffing? And down here, I have the inference from the pressure field without the mask and with the mask, and we also have the velocity field. We approached LaVision, which is a big company in Germany, and now we wrote this paper on the espresso coffee that I showed you earlier. They use this technology, they use lasers and so on, but this is basically looking at thermal gradients from this puff, and we can go now just from the data, the noisy data, the real data. What you're looking at is this Dr. Thomas Berg, that is our co-author now. So I'm just trying to demonstrate that with very simple concepts, you can do very practical things like this one. Here's another practical application. We work very closely with Air Force. The Air Force is interested to see if the wings of the airplanes have holes, like this one has a crack. It's a surface crack, so they have this ultrasound testing of their materials. This was actually what you see here on the left is the real ultrasound data on the right. is what the pin is trying to do, is trying to mimic this data. In the process, as the ultrasound hits a crack, you see this diffraction wave, very complicated wave system. We only use 10% of their data, and we use the physics. The physics is very simple here. It's a wave equation with a variable wave speed, c square, which we can infer. We can write a neural network to infer the velocity, which is now a function of space. Here on the upper right, we quantify that. We only use 10% of the data. This was a hackathon, 12 teams at DARPA. They competed for this. My team was the only team to win this. We didn't get extra money, but we can brag about it. We can brag about it because we use physics to improvise. We also had to develop something new, and that was the concept of adaptive activation function. I told you about this sigma that takes a linear base, a first-order monomial, and make it a nonlinear basis. Now, in the standard neural networks, every neuron fires at the same rate. However, in real applications, you don't want that. So what we did, one of my postdocs did, is to introduce an adaptive activation function, parameterize this hyperbolic tangents or sigmoids or ReLU or leaky ReLUs, so that every neuron fires at its own rate. So you introduce this parameter A, which becomes a hyperparameter similar to the weights which I have here and the bias. So A is the number of neurons, which basically defines every neuron will have its own activation function. Of course, you can learn from scratch the activation function, what's the best one, but this is very time-consuming. Here, the number of weights is millions or millions. So if you add another thousands of parameters, it doesn't really matter. These are all highly over-parameterized networks. So the main idea here is that I can use adaptive activation function. Every neuron, every layer of neurons could have its own firing rates. And you can see the difference here. When I try to approximate a function like this, is a function on the left, the spectrum on the right. If I use the standard activation functions, I cannot really train this network. However, if I use adaptive activation function, you can see here this green color, this olive color is compare the top to the bottom, and then you compare the spectrum on the right. You can see I can resolve the entire Fourier spectrum of the function. What happens here, basically, the standard activation function will lead to a bad minimum when you do a steepest descent. However, if I use this activation function, adaptive activation function, I can get out of the bad minimum and find the true minimum, and therefore I can train the system. So we have developed some theory with that, with a collaborator from MIT, the CSAIL group, computer science, where basically we prove that adaptive activation functions eliminate bad minima. Of course, this is a big deal in neural networks because the main, and that's the holy grail really in neural networks, is how do you avoid bad minima? And how do you go closer, not necessarily at the global minimum, but closer to a global minimum? If you eliminate bad minima, there's so adaptive activation functions do something like a second order steepest descent, if you like, but without computing the Hessian. That is the very expensive part. Of course, many famous people in neural networks, Mike Jordan from Berkeley and others, advocate use second order methods when you use neural networks for the gradient descent. However, these methods don't work unless you are very, very close to the minimum that you are targeting, and you have to compute the Hessian. Adaptive activation functions avoid that at the minimum cost, probably 5 to 10% extra cost. I want to take a break here, summarize what I told you. I just show you one version of pins, the standard pins and the X pins. However, my team and other teams have developed pins for conservation laws, variational pins for stochastic PDEs, fractional PDEs, and so on. I want to show you briefly how we do stochastic PDEs, because it involves another neural network, and that is a beautiful neural network, a beautiful concept by Ian Goodfellow, who was a student of neuroscience at Stanford when he came up with this idea of training a neural network, which we call discriminator, by using a competitor, and the competitor will be a generator. So this is a case of not supervised learning, but semi-supervised learning. The network sees new data, that's the real data, but also has to discriminate against fake data. You've heard in the last 4 years, you've heard about fake news a lot. I hope that after the November elections, we'll never hear about fake news again. But this is a concept that fits very nicely adversarial training. So the generator generates fake data very close to the real data. Discriminator now trains itself in a sort of game theoretic approach where the generator and discriminator play a game. So this way the network can be trained much faster using the real data. So that's why it's called semi-supervised learning, because we don't need as much label data. Now the generator uses noise of some dimensionality, and we prove in this paper that I have here in Scientific Computing that using appropriate dimensionality of the noise, you can actually mimic any stochastic process. If you do that, then you can proceed to modify this GAN. We call this physics-informed GAN, because you can have a generator for this problem. Let's say you are looking at a simple stochastic PDE, like in porous media, where you have a hydraulic conductivity, you have the velocity here, and these are all stochastic fields, and the right-hand side. In this problem is unusual like the stochastic PDEs because I pretend that I don't know exactly the right-hand side. I have a few measurements. I have a few measurements on the unknown solution, and I have a few measurements on the conductivity. Okay, so this, depending on the correlation length of this stochastic process, this could be dimension 5 or it could be dimension 10,000. If it's white noise, of course, it's a different type of stochastic PDE. But this stochastic PDE is with correlated noise. We set up a GAN where the generator is for the conductivity, for the velocity, generator for the right-hand side. So now the discriminator here will see this generated data from the stochastic PDE. We'll also have these measurements, and by iteration, you can solve this problem. One of the things that we observed in this work, and I don't have time to explain everything, is that although we don't exactly beat the Kirchhoff dimensionality, we were able to do 120 dimensions. And in fact, one of the real applications, we did 10,000 dimensions. And the reason for that is it's expensive, but it's not exponentially expensive with the dimensionality. It's more like linear or quadratic. Let's say if you go from 100 dimensions to 200 dimensions, the cost will go up by a factor of 4 or 5, not exponentially. Another idea of variational pins, and those of you who work on variational methods, finite elements, and so on, you will appreciate this. This is now a Petrov-Galerkin projection. Think of solving this 1D Poisson equation, and here I write the residual, where now the trial space will be the neural network space. It's a non-linear space. However, for the test space, the test functions will be polynomials. I like Legendre polynomials. I use Legendre polynomials. I'm sure Claudio Canotto may like the same things, spectral methods. But basically, I can create some sort of a spectral method where I have a Petrov-Galerkin projection. The trial space is this nonlinear space, and it is a nice space because people have proved by now that this nonlinear base works like adaptive finite elements, if you like. So you have this neural network benefit, but also you have the smoothness of polynomials, so you can transfer derivatives to that, and you can do integration by parts, you can do discontinuous Galerkin. What I want to show you here is that if you use signs, and signs are legitimate test functions here, but also legitimate activation functions, then for this single neural network, you can write simple expressions of the residuals, and you can actually stare at them and say, well, look, this is really a different method. Look how the residual looks. If I look at my Petrov-Galerkin using a standard space, it will not look like that, and so on. And in fact, you can gain accuracy. The problem here is you need to integrate these integrals, and of course, you have to go either to Monte Carlo or Gauss quadrature and so on. So you have to introduce auxiliary grids. And as I said, I don't like grids. I talked about lots of applications. There's a lot to do in math. Your seminar is you're right to focus on math, because I think the next big breakthrough will come from looking at math, pragmatic math, I should say, math that follows applications like these ones where you actually solve real problems. I talked about the nonlinear approximation theory, optimization. I show you how adaptive activation functions, for example, could help in optimization, learnability, and how small data set, generalization, and so on. I want to mention these two papers by Sid Misra from ETH. I gave a talk a few months ago there, and Sid actually produced, after listening to my talk, he produced some really nice papers where he used well-posedness to justify some of the work that we've done in terms of convergence, in terms of ill-posedness, and so on. I just want to give you an idea of what these errors are here. If you can see the schematic, Andrea, can I ask you to give me a thumbs up? Can you see the schematic here?
Yes.
Okay. So what I have here in this box is H is the hypothesis space, is the neural network space. So you see the neural network is the truth solution is here, U star. So this is the approximation error. When we say these universal approximation theorems, they talk about this distance, okay? So let's say I minimize this distance because the approximation theory says that if I have a big network, lots of layers, lots of neurons, I can make this arbitrarily small. That's great. This is where we use 2 infinite elements. However, I have this generalization error. What is the generalization error? Well, I have an objective function, which is an integral, and I have to make it a sum. And I have to sort of do a finite sampling. That will be a generalization error. I commit a crime here. Another crime I commit is I have now a loss function, the objective function, which is, unfortunately, non-convex in terms of parameters. It's high dimensional. Do we know how to find, and do we have any guarantees that we'll find a unique minimum when I optimize a non-convex high dimensional loss function? The answer is obviously not. Stochastic gradient descent that people are using have been tremendously successful, maybe for the wrong reasons, but many times it's not so successful. Many times the solution will lock in to a local minimum. So as I said, here when you develop theory, you actually have to tackle the approximation, you have to tackle the generalization and the optimization. The approximation, I think, from the mathematical point of view, is perhaps is easier. The generalization and the optimization are the big elephants, the big beasts. This is just some reference to my work of actually my collaborators. So this is in the archive. You can take a look at it. I think this is the first paper that shows convergence and generalization results for pins. Basically, we're trying to we zoom in specifically on elliptic and parabolic equations, quasi-linear equations with the standard networks. But we show something interesting, which we see from our experiments. We see, for example, that we can solve boundary value problems without boundary conditions, and we have convergence in the L2 sense. Now, we may have data somewhere else, or we may not have any data, but we see convergence in the L2 sense. Not fast convergence, but we see convergence. Then we see that if we introduce these boundary conditions, initial conditions for this type of linear PDEs, we can improve the convergence to H1. More recently, we use, in this other paper, we haven't released this paper yet, but it's about to be submitted to the archive. We use a very different approach, and that is the equivalence of norms and compactness arguments. And we try to have both a priori and a posteriori error estimates using, for example, these are just an example of the loss function in the discrete formulation or the continuous formulation. So using arguments of stability, sorry, I didn't mean to jump in, of stability. Here, capability of a neural network means expressivity, that the approximation error goes to 0. Now, if you work with discrete neural network, discrete approximations, you also have to assume that you have generalization. So then you can also show convergence. There's probably less than half a dozen papers right now on the theory of this. So this is an opportune time for people to jump in and do really good work on as I said, on on different variations. In this, for example, in this paper here, we also have the domain decomposition. We developed something equivalent to spectral elements, but with Petrov-Galerkin flavor and neural network spaces. I don't know if you can see my movie. This is my interesting movie that I show you today. This is a real example, real application for the Navy. Andrea, can you see this movie?
Andrea, hai il microfono chiuso.
Okay, sorry. Yes, we are seeing the movie regularly.
Okay, because there's sometimes buffering. So this is a U.S. Navy destroyer going through North Atlantic at waves which are 20 meters. Okay, now as you may have heard, there's the concept of digital twins. People want to develop autonomous airplanes and cars and also destroyers for good reasons. And so the question is, can you predict, using any methods, computational methods, can you predict the motion of this? It is subjected to a stochastic sea elevation. The elevation of the sea is stochastic. We use a real spectrum of the North Atlantic. And so I work with this with MIT people who are very patient. They have students who can do simulations for weeks. In fact, it takes 1 week to do one simulation like this using CFD solvers like OpenFOAM. We need a lot of data to pre-train network. But we want to basically train neural networks offline and then use them online. So I want to be able to approximate functionals, which will give me the time series of the response of the vessel given the stochastic elevation. So I looked for theory, and I found this theorem by Chen and Chen from Fudan University, which was very few people. And I would like to know in this audience, if anybody has seen this theorem before, I would be really pleased to hear. But I checked around, nobody has looked at this. And it turns out that there is indeed a universal approximation theorem for functionals. And it's down here for the 1D case. U of x will be my stochastic elevation. Then you have this series. This is from the input, which is now a function. And the output is a function, is the response of the vessel. This also could be extended in... this was written in an IEEE journal, Electrical Engineering Journal, so mathematicians didn't pay attention to it at the time, and the engineers couldn't understand it. But it turns out that using standard, you don't have to design neural networks. Like this, the current neural networks with some memory, what's called the LSTM, long short-term memory, recurrent neural networks, could work fine. In fact, more recently, we use something that Google used for natural language processing, for translating text, what's called sequence to sequence, which are two LSTMs back to back, an encoder and decoder. So I can use from the left here, I have the stochastic elevation of the sea, two different elevations. And I can predict, if I pre-train this network, and that's the hard part, pre-train it. But as I said, I rely on patient MIT students to do this. Then I can predict the stochastic response, the rolling of this, and you saw the rolling is not trivial, the heaving and so on. So here I show you some results. This is now for new stochastic elevation of the North Atlantic Sea. I predict, and as I said, the CFD takes 1 week for one simulation. The neural network takes 0.01 seconds. Okay, so the left is 1 for 3 degrees of freedom, 1 stochastic elevation, a second stochastic elevation. You cannot really distinguish the CFD from DeepFNet. And that's what it's all about when you do autonomous cars and do it fast. Now I want to move to something even higher. And I gave this talk recently. I give this talk a lot to different communities. One of the communities I talked to was neuroscientists that actually you may know, a very good friend and Italian, Tommaso Poggio. Tommaso Poggio is my favorite guy at MIT. He's not only a physicist, a great physicist, a neuroscientist, he's also a great computer scientist. So he invited me to give a talk at his center at MIT a couple of weeks ago. His center is called the Center of Brains, Minds, and Machines. So I started with this talk and I said, look, we all strive for intelligence. true intelligence requires abstraction. True abstraction requires expressing that intelligence using operators, not just functions. So the question is, can we use neural networks to approximate not functions, not functionals, but operators, non-linear operators, maybe continuous operators. Discontinuous would be great too, but non-linear operators, because you don't want to teach a robot calculus the way we learn it. If the robot has to go through the same process that we went through, if they want to have intelligence or collective intelligence or compute anything, they have to carry an exaflop computer on their head, and that's impossible. So we need some possibility to approximate an operator. And here again, I found this paper that was probably the best kept secret, again from Chen and Chen. It so happened that Tianping Chen, who is retired now professor from Fudan University, sent me an email 2 days ago because he realized I actually discovered his theorem. And this theorem now says the following. It's for a single layer, like Saipenko's theorem. It says that if you want to approximate a nonlinear continuous operator, where the input is functions u that you pull from this compact space V, and the output is, of course, functions, then indeed there's a universal approximation theorem. And the theorem is down here in these big brackets. It says that G, which is the nonlinear continuous operator of U, which is the input, Y, which is the space of the output, can be approximated with this double sum. Arbitrary close for any function U from the compact space V and so on. Now, as I showed you earlier, when we talk about neural networks, approximation is one thing, the other one is generalization, the other one is optimization. So the theorem was there, but nobody actually implemented it. Nobody knew about generalization, unseen data, and of course, can you train it? Because now you have to train a network that you have operators, you have functions. More recently, my team, this is a theorem that will appear in a Nature paper, Nature for Machine Intelligence. It was just accepted our paper, so you will see this theorem. We extended this for deep neural networks. So now you can see I still have a composite neural network, something we call the branch, but that's now a deep neural network. It actually could be something else, could be radial basis functions or something else. And also a track network, okay? So it basically says the same thing for deep neural networks. So now we have deep neural networks to approximate operators. But how do they look? So this is really an important topic, I think, for everyone, for every community. So let me set up the problem properly. U is the input function, not just data, but functions now, okay? So I go from a function to a G of U, which is a function. So the way I want to set this up is, let's look at the panel B here on the lower right. It says training data. I want to take a function U. I want to observe it or sample it or measure. Sensors would mean these points M, another different function. And every time I have an input U, I observe G of U. Notice that I observe U at many points, but I observe the output at a few points, because that's practical, okay? This will be my labeled data. This is for training only. And then eventually, if I go to this panel A, eventually if I train G, then you come along and you give me another function, and you ask me, what's the output? What's G of U of Y, okay? Now, how do you make this practical? Well, there are many ways to represent this space V, the input functions, the space of input functions. But this is the simplest one. Let's say you sample this function U at uniform points and so on. You can do better. You can have functional representations. In fact, U, since it's a function, can be represented by a neural network itself. So there are many different ways. I will show you different ways. But this is the simplest way. So let's say I use as my space V a function which I represent with a Gaussian process with this Gaussian kernel. This Gaussian kernel is characterized by a correlation length L. The smaller, the better, but the training will be better. But you can see now that I can come up with this kappa, which depends on the space, the number of points, and I can find an upper bound which goes as 1 over m squared. M is the number of sampling points. L squared, which is the correlation length. And I have a theorem here that says that the supremum of this u of y, where u is from this space, when it's represented by this neural network, is bounded by kappa. In other words, you cannot do better, of course, from sampling the space v. So how you present the space v is important. Now, this is a neural network that I want to show you. I put here, for your convenience, the mathematical expression for the neural network. And down here now, I show you 2 neural networks. Look at the one that says D, unstacked DPONet. The upper part is the implementation of this big parenthesis, which is associated with the input. U of x, sample at points j, m at m points, is my input, but it's a function, right? I truncate somewhere. Then I have this output space, which I call the trunk net. So the output space itself is a neural network. I have p points here. The first sum is from k equals 1 to p. K is here, as you can see in the trunk. I cross them, I take the inner product, and I compute g of u of y. Okay, so this is a neural network that we propose. We call the branch trunk network. It's a DPONet. This is what we call DPONet, O for operator. The big question is, you can approximate this an operator arbitrarily close. How about generalization? In other words, if you test this for new data, how good it is. So I want to show you a very, very simple example. And so the issue is here, can I learn an operator which is a one-dimensional integral? So I want to learn this operator 0 to x. So x is from some interval from 0 to 1. It could be from 0 to 100. So the way I will train this network is I will assume a lot of integrands, u of t, which I take from a space v, let's say from Gaussian random fields. I take as an input. I observe the output, not at all these points. I cannot afford to observe the output s of x at all these points between 0 and 1. I actually observe, I take 10,000 of integrands, and I only observe s at 1 point. So for the first u, I have s of 0.1. Second u, s of 0.2, and so on. Now, down here in panel A, I have the mean square error. I have the mean square error for training, and I have mean square error for testing. Testing here means you give me a new function, which I haven't used, and then I try to predict. And you can see this in these curves. The training error and the testing error are very close to each other. That's very good. It means for this DPONet, my testing error is as good for unseen data that I have not seen before, is as good as the data I used to train it. Here on the right, I show you different neural networks. The curve on A corresponds to the unstacked, the last one that shows that the testing error is slightly above the training error. The smaller the difference between the red and the blue is the better. A standard neural network, which I call here FNN, for feed-forward neural network, is, you can see, is a big difference. So it doesn't generalize well. Even sequence to sequence, which we use, doesn't generalize well. This is another application. Now I have the operator. By the way, I use here the PDEs just to generate data. I pretend I don't know this, right? I learned this. So here what I will learn is I will learn a map from u of t to S1 and S2. You see a single input, one function. The output now has 2 functions. Again, you can learn it, but I want to show you something, especially for those of you who are interested in exponential convergence. I plot the mean square error versus the training data. And what do I observe here for this neural network? The convergence rate is exponential initially. And then at some point, it transitions to very slow convergence. In fact, as I change the width of the neural network, the number of neurons from the left 50 to 200, you can see the arrow. The transition points from left moves from left to right. So in other words, this DPONet can learn in principle exponentially fast. Unfortunately, the size of the neural network makes the convergence saturate. But in principle, and this is where there's an opportunity for all the smart young researchers and students, they can come up and design a better neural network than DeepONet that can learn exponentially fast. Moving on to a PDEs, you can see what we do. We observe this. We observe the input. Here's some excitation force for this reaction diffusion equation. Then I observe at very few points. This is the XT domain where I have labeled data. This is the output. Now, this could be the real measurements. This could be a solver, numerical solver that you have. But basically, you can train this neural network, and you can see again, as you train with the number of points or the number of functions that you use, the training error and the testing error are basically the same if you converge. Now, after you learn this PDE, again, I don't use the PDE here. I only use it to create data. This could be real measurements. This could be from sensors. But I learned that PDE. After I learned that PDE, I can make predictions very, very quickly at a fraction of a millisecond. And now this part here is for my friend Francesco Mainardi. I didn't know that he would attend, but for those of you who have followed my work recently, I like fractional PDEs. I like fractional calculus. And the reason I like fractional calculus is the same reason, not because I love Francesco. I love Francesco, that's true. But I see something in fractional calculus which is very similar, like an analog, to deep neural networks. Everybody talks about the expressivity of deep neural networks. And the parallel with fractional calculus is that fractional operators, with all their disadvantages, are very expressive, especially in the big data era. So here I want to demonstrate how I can train a neural network to learn a fractional operator. For example, the Caputo derivative. Caputo was the advisor of Francesco. So let's say you have all these functions, and we have formulas to compute the derivatives. We can actually use the existing technology, and I have here the framework, how I input these functions into a branch, how I have my output space, and I can learn this. So as I said, let's apply this to 1D Caputo derivative. The Caputo derivative, for those of you who have not seen it, is this integral. Okay, the derivative is inside, the Riemann-Liouville derivative is outside, but you can see there's a singular kernel and it's an integral. Okay, so now the question is, remember I told you about this space V, the space of inputs? What is the space of inputs? In fact, what I used before is a GRF. GRF violates the theorem, because the theorem, to prove the theorem, I needed a compact space. GRF is not a compact space, but I proved numerically that actually it's pretty good space. Can I find a better space? And here I represent the V using a GRF. These are the green curves. Okay, and you can see I do reasonably well as I learn the number of iterations, but I can do even better if I use a spectral approximation to represent my space of functions, U. In fact, I use polyfractonomials for those of you who have followed my work, but even Legendre polynomials is doing pretty well here. So the green line is one representation of the V space, namely GRF. The blue and red lines is using spectral approximation, using model representations. And you can see I gain more than 2 orders of magnitude. So yes, I can learn the Caputo derivative, and then I can spit out the answers in a fraction of a second. I don't need to do these operations. So that saves me tremendously. I can even do better. I want to learn the fractional Laplacian on a disk. What is my V space? Here now you can see I use another type of polynomials, the Zernike polynomials, which are the best polynomials on a disk. And I use actually not a lot of polynomials, this pyramid of polynomials. This is my space V. And yes, indeed, I can learn this very fast. Now, this is one of the cases that I use a standard convolutional neural network because the space was simple, so I was able to map it to make an image. Just like people who are doing imaging, they use CNN, convolutional neural networks. I use a convolutional neural network instead of my DeepONet. So I challenged my postdocs to find to beat DeepONets, and they did actually. But CNNs are only for good canonical domains and so on. So what I'm suggesting is that although DeepONet is pretty good, there are other neural networks that can be better. Here I show you I can solve stochastic PDEs, where I truncate. I can find, but basically we can learn stochastic operators like fractional operators and so on. I don't know how much time I have.
I guess still 5 to 10 minutes.
10 minutes, okay, great. So I want to show you that DeepONets can learn really complex operators. And that is one of these is the Euler equations with non-equilibrium chemistry, which even for standard conventional schemes are difficult. What I show you here is 3 species, high Mach number, and these are data generated by a WINO scheme that my colleague Qinwan Xu here gave me a code to generate the data. But because of the chemistry, you take extremely small time steps. This is multi-rate dynamics. It's very common in hypersonics, supersonic, hypersonics now. So I want to learn this. I want to learn it and use a DeepONet to learn it. So what I do, I take the data, I generate 100 trajectories for training and 50 trajectories. I will not use those, but just for testing. So you see here, I train neural networks for the equations for nitrogen, for oxygen, for NO, and so on, for velocity and temperature. Any one of these conservation laws that I have here, I will encode and learn it offline using data from these CFD solvers, okay? Now, after I learn that, I want to make a new prediction. Now, what's the input? The input is down here, is the initial condition, is the jump in the Riemann problem, is the smoothness of the jump, which I parameterize using this hyperbolic tangent, and I let eta being in this interval of 0.02 to 0.2. In this interval, as you can appreciate for this complex multi-physics, multi-scale problem, I can generate a lot of data. And now can I predict very quickly and how accurately? Here I just show you one example that I can predict from initial conditions like that. I can predict in a fraction of a second what will happen at specific time with accuracy 10 to the minus 5. You can see the loss for this testing and the loss for training very accurately. So this is now thousands of times faster than using a CFD if you pre-train the DeepONet. I want to show you some theory that we're trying to do using these DeepONets for conservation laws like that. It's very difficult. It's more like the failure so far, I want to show you, but basically you can see here that we're trying to find a bound now, an upper bound for the representation of the neural network for this type of classes of conservation laws. And we have a bound that depends nicely on 1 over m. M is the number of sampling points of the inputs. 1 over p. P is the number of the points of the output. Then I have here the trunk, 1 over the number of neurons of the trunk. Unfortunately, I have a term here which is nice. In the n is 1 over n. B is the branch network. L is the number of layers. But I have this nasty term, square root of m, which messes up my convergence. There's some technical arguments here. I don't have time to talk about it, but I want to show you that we are concerned about convergence, and there is, again, opportune time for young people, ambitious people, to come in and make a splash using doing theoretical work on this. I want to finish with DeepMNM because, as I said, it's a nice and I didn't show this. This is a DARPA project we have. I didn't show it to other people. So basically, it's simulating now a real case with dissociation of air and so on. This is work with Johns Hopkins University. It's currently DARPA, similar as before, Mach number 8 to 10, and we use the DeepONet to pre-train it. So from the velocity and the temperature, it can give me chemistry. You know how important that is, because the chemistry, if you do chemistry, and here I have 5 species. If you do chemistry, the time step is ridiculously small. It's microseconds, okay? Here, you go with milliseconds. So So even CFD solvers take forever. So this is the data I use in Mach number 8 to 10 to train my network. And then I use new data to predict. Here's the prediction. I can predict from velocity and temperature. I can predict, you can see here, density of O and then O. They vary by 8 orders of magnitude, and I can predict it in 0.01 second. I can predict from chemistry, I can predict the velocity. And then we have this. This is my last acronym. I'm not going to give you a promise, no more acronyms. This we call it DEEP M&M. It's multi-physics and multi-scale. You use this pre-train off the shelf, like you know, if you try to make a toy with Lego, you put them together. DeepONets is my pre-trained neural networks for every one of these species, and I have measurements only on the velocity and temperature. It's very unlikely that anybody will give you measurements when you have hypersonic applications on the chemistry. So you have to predict the chemistry. You have to do it very fast at hypersonic speeds, but you have some measurements. So I set up a neural network. Everything this is done really, really quickly, and you only need to assimilate 4 or 5 measurements. So you have a loop here, and down here my loss function is one part that constrains the operators and one part that constrains the data. This is just a regularizer, but you can see now, you can learn this very quickly. How, and here I have some data. I show you that indeed we can learn very quickly unseen data. How quickly can you do it? Here I compare with, and this is 1D in space, okay? In 1D in space, we are 50,000 times faster than CFD with this. And the accuracy is comparable 10 to the minus 5 to the CFD. So let me finish how I started with this coffee. As I said, we use real data from Schlieren photography, 3-dimensional data. The data is here, just on one plane. We learn exactly, the neural network will learn exactly the data on thermal temperature, but then we can also infer the pressure, and we can infer the velocity. In fact, when I saw this data, my postdoc showed me the velocity over my cappuccino, the maximum velocity, he said, is 0.4 meters per second. I said, that's impossible. Then this aroma of the coffee will hit me right away, but it takes a while. It's more like diffusive process. And we talked to the experimentalists, and they said, yes, it's not 0.4 meters, it's 0.08 meters per second. And then they didn't believe their own data, and they went back and they did another experiment with particle image velocimetry, again on, on a different cup of coffee, and they found that the maximum velocity right at the center line is 0.4 meters per second, what neural networks predicted in a blind comparison. So I'm very happy about this experiment. Finally, we wrote a paper. We just submitted it to Journal of Fluid Mechanics. I think the first paper, coffee flow over an espresso cup. And I'm very happy to share this with you, my Italian friends. And I just want to finish with this paper. For those of you, the students who want to learn this, we have a SciAm review paper on the archive, which will appear also in the journal. But also there's this library called DeepXDE. It's a free library from GitHub. It has 56,000 downloads so far. X is for anything, because you can dial in on ODE, PDE, and fractional PDE, and so on. There's some simple geometry module and so on. And also I want to thank my sponsor. If you want to learn more about it, I direct this nice center. This is a center I started as I think it's the first big center on physics-informed learning. I started this 4 years ago from the Department of Energy. I'm the director. We have good people from Stanford, MIT, Sandia, and the Pacific Northwest National Lab in Santa Barbara. But you can find a lot of papers on this. When we started this, actually, our proposal was rejected by the Department of Energy. I was talking about scientific machine learning and so on. It was rejected. We submit again. Finally, they were convinced. Now the Department of Energy is starting a new initiative on physics-informed learning and scientific machine learning, and they are spending $200 million in doing that. So I'm very pleased. Usually, new ideas, especially if they are simple, are not accepted. But as I said, there is also a lot of work for mathematics here. So I would like to thank Andrea for inviting me here. I'm looking forward to visiting in person. I'm looking forward to also interacting with any of you who are interested in this material. I give this week I give 3 talks on this stuff. There's a lot of interest from diverse communities, from geophysicists to astrophysicists. So anyway, I'll stop here and thank you very much.